Yes, sir.
All right, so we have to first let's talk about those two exercises which I gave. On Devyani submitted the the 8 queens and queens. What about the others? Are you dry? You have to do those two exercises. I mean, if you want, we can make it as a uh, assignment, but the point is that all 52 all will have to submit in Piazza. Hello. So what is your status of 8 queens and knights tour? Hello. Can you give more time? I was not able to complete. Yeah, you can take more time. You also try to give a graphical front end to that. Yeah, you will be able to find very simple graphical front end where you can draw, for instance, a chessboard, and you can also draw lines. Yeah, for Knight's Tour, you try to do something like that, so that one can visualize the Knight's Tour. You understand what I'm saying? Okay. All right. So, yeah. So now let's quickly recall what is happening in this lecture, the lecture 11. Can somebody summarize?
Yes, sir.
Yeah.
So, in this lecture, they talk about data abstraction and modularity.
Yeah.
The basic thing is they talk about they take an example of table and
Mhm.
create that table with an associated list. But then the problem arises that the operators, the functions that we can use on an A list can also be used by the user. So there is no abstraction. So
Okay.
then they abstract all the, like, they create a tag, they abstract all the, so that no other function can act on this table, so that creates a data abstraction barrier.
Okay.
Then they talk about hash tables and how hash tables can make our, like, how we can dissociate implementation so that we can anytime change the implementation while keeping the contract the same with the user.
Mhm. Okay. Yeah. So and a particular thing is that they use they use operation set cadder. These two operations. This set cadder to implement the abstract data type. Yeah.
Yes, sir. Set
Yeah.
cutter was used.
Yeah. So what is the set cadder? If I have a list.
Sir,
Yeah.
it just it takes my pointer and takes it to point the first element from the associated list. The once we have last const.
Uh, can you be more precise? Can you tell me once more?
So in the associated list, we may add a value. So what this does is we have created a tag with data like table. So
Yeah.
what it does is that it takes the pointer of that table and sets it to the latest added element, so that we have a nice structure.
Yeah. But if I have a random list X and I say set color of X and then some other list, what will happen?
So it'll take the care of X and then make the other list the color.
So the set color and set care operations are not functional operations. Hello.
So what is meant by that? Not functional operations.
So functional operations means that when I say y is equal to f of x, yeah, y is equal to f of x. Every time you say every time you say f of 10, it will have the same value. Yeah. Yeah. Let's put it this way: an operation is functional.
Sir, your screen is not visible.
Yeah, sorry. Sorry. Can you see now? Yeah. An operation is functional whenever if the same input is given, the output is the same. Yeah, agreed. That is what you mean by function. Yeah, when I say f is a function, what you mean is that for every x there is exactly one y. So every time I say give the same x, I'll get the same value y. That's what you mean by a function. So an operation is functional, or a functional operation is whenever you give the same input, you should get the same output. Now, if I have, let's say, so imagine I have this define so what I mean here is that so when I do the set color operation, I have a state here. Yeah, my x is actually the set 1 2 3 4. Now when I come here, my x is actually 1 1 2. Yeah, because I have so x is the list. X is the list 1, then the list 2 3 4. Yeah, x is this list, this pair. Now what does set color do? Set color changes that the color part of this list, color part of this pair to 1 2. Yeah, so the basically what it says is what it does is that it changes the state of the variable. You understand what I'm saying? So in other words, set color operation has a side effect. Okay, maybe more than functional, this is the more appropriate thing, because what happens is that in the case of set color, it never returns any value. Yeah, set color of anything, it doesn't return any value. So so therefore it is more appropriate to talk about it as functions which have side effects. Color, yeah, operation has side effects, set color and set char. Yeah, so similarly, if I put set char of 3x and 3, what will happen is that I will have current list is x is actually, I should not, 1 1 2, and it becomes x will become, the 1 will be replaced by 3 and 1 2. Yeah, I should put a, yeah, so it will become 3 1 2. Okay, so those are this. So these are these operations of side effects. So far, many of the operations we had didn't have any side effect, except define. Define had a side effect that it actually brought into existence a variable binding. Okay, apart from define, No, but define is just a name association. But apart from that, it didn't have any other effects. But for the first time, we have operations which have side effects, and we are using side effects to actually implement ADT. Okay, abstract data type called hash table. All right. So Siddharth, yeah. So did you finish what the summary?
So yes, sir. Like
Okay. So now let's try to. So what is the big idea? I mean, the one thing which we learned, they actually use this. What do they use setchar and setcadder for?
sir, I didn't get the question. Like, what is the exact question?
Yeah. So what is the purpose of set? What is setchar and setcadder used here for? So basically, my point is that they create abstract data types,
Yes, sir.
data type called hash tables. Yeah, and how is this hash table used? So I will name a hash table like table. Okay, it will be called table. Now that table hides a lot of things. That table name hides, it has a type and it hides a lot of details. And the point is that to operate on that data type, all I need to know is this table. Okay, and once I define this table, then I will actually use setchar and setcadder to modify this table. Yeah, so that is what is happening here. This is the second implementation. In the first implementation, if you look here, can you see my screen?
Yes, sir.
Okay. Where is it?
Sir, in the first implementation.
Yeah, it's the first implementation. It's here. Yeah, table put and table get. Yeah. So what they're actually doing is that the table is one name, which actually points to one data structure. And then whatever operations I do, I am actually using the same name TT1 for that table. And then I am changing the internals of the table. That's what is happening here. Yeah. And that is what you use setchar and setcadder for. And so ideally, the side effects is not a very good idea, but because their programming language, but you cannot live with side effects also, because whenever a print statement in a programming language is an example of a side effect. Without print statement, we cannot have we cannot do really programming. Yeah. So, but different programming languages have different philosophies. Even though Lisp is a functional language, Lisp uses side effects. But on the other hand, languages like Haskell, for instance, does not have any side effects. They don't allow side effects. In Haskell, this kind of implementation won't be able to, you won't be able to work this kind of implementation. It will be difficult. Okay.
So,
Yeah.
so I didn't understand what are side effects and what are not side effects.
So side effects are, so imagine you have imagine you are programming. Yeah, what is your state of a program? What is state of a program? What is the state of a program? So state of a program will be, let's imagine your program manipulates files, sockets, then all kinds of things. Yeah, I mean, within a program, you can manipulate a lot of things. You can manipulate files. You can manipulate input output stream. you can manipulate sockets, you can manipulate variables, you can manipulate uh, uh, memory, and so on. Yeah, all these are different parts of the program which you can change from within your program. Now, so imagine you have an operation like x is equal to you have a program like x is equal to x plus 1. Okay, this one has a side effect. This is an assignment operation. Okay, this has a side effect. Has a side effect. What do you mean by that? So if let's understand what is this x equal to x plus 1 comes at some particular point in the program. Just before you encounter this x equal to x plus 1, you have a program state that includes the state of the files, the value of the variables, the value of each memory location, the content of each socket, and so on. Yeah, that if I imagine that is my state of my program, then after I encounter x equal to x plus 1, something will change. What is that will change? The value of the memory location x will be added by 1. Yeah, it will go by 1. Yeah, it will increase by 1. So what has happened is that this program statement has changed the state of the program. That is called a side effect. Okay, or if you say print hello. Okay, this one changes the state of the output terminal, output stream. Yeah, because earlier whatever was there, now hello will be added to that output. So it has changed the state of the program. Now this is very different from let's imagine a statement like so you agree that these two statements change the state of the program? That much you understood, Nidesh?
Yes, sir.
Okay. Now, so far, before char and cadr, whenever we were programming, for instance, when we wrote a factorial function, there was no change of state of the program. Yeah, you were having an expression, and our model of a computation was I am given an expression, and each step I'm rewriting that expression. That's what our model of a program was. Yeah. So
Yes, sir.
there was no state of the program as such. I mean, of course, we had names, but names were just, you saw that the names were nothing but syntactic sugar for lambda expressions. Yeah. So when we said let expressions can be written as functions, we observed that some time back. Yeah, whenever I have let x equal to 10, y equal to 20, and then some expression, I could write it as a function which has input parameters x and y, and then the expression called with x equal to 10 and y equal to 20. This one we observed. So therefore, the local variable by names which we had, we could eliminate all of them completely, because what we could do is that we could take the entire program and we could just substitute wherever a name is used, we could substitute the corresponding expression. And that will work because we didn't have any side effects in our program. Wherever, for instance, if I don't have setcadr and setchar in my program, and imagine I have defined x equal to this one, then what I could do is that I could actually control x, control v, wherever x is used, I could substitute this list 1, 2, 3, 4. In all the programs which we wrote so far, I could do this. Whenever I had defined something, I could actually substitute the first value by the second value, and that is because none of the statements we talked about had a side effect, in the sense that this was not happening. The state of the program was not changing. I was not manipulating any variables. I was not writing anything to the output and so on. We didn't actually write anything to the output. Yeah.
Yes, sir.
So that kind of program is called side effect free programming. Okay. And so the advantage of functional programming is that side effect free programming is that the debugging is so easy to do, because once you run a program, once you debug a program correctly, then you know that there is no state of the program, and every time I will run the program, it will have the exact same execution. So there won't be one. If I don't catch any error now, I will not catch any error later. But this is not true for programming languages like C or Python or any, even in the case of Lisp, when you use side effects, what will happen is that there is a, whenever you run a program, you can ensure that with the current state of the program, it will be working fine. With the current setup of the files, with the current content of the sockets, the current input, it will work. But you can never be sure that with other inputs, with other state of the files and other contents in the sockets, it may not work. Okay.
Yes, sir.
So that is the general advantage of functional programming. That is, but then again, you could completely eliminate with x equal to x plus 1. For instance, Haskell does not have any assignment statements. Okay, there is no assignment, but this kind of things you can never avoid, because I mean, if you want to print something to the user, how do you print? Now, what languages like Haskell does is that, so it understands that this is a side effect, but then this side effect will be incorporated into the state of the program. Okay, I mean, in a sense, this side effect will also be considered as part of the functional language. For instance, this side effect will be seen as a function which takes this state of the world. So if the state of the world in which we inhabit, if the state of the universe is the same, then print hello will return the same value, will result in the same world. That is the approach which Haskell will take. And yeah, I mean, one day I'll show you what is the approach of Haskell to solve this side effect. Okay. Yeah. All right. Any questions? Maybe I was a bit. Any questions? So you see that this setchar and setcadr almost works like x equal to x plus 1. Because x equal to x plus 1, what does it do? It just takes one state of the value, one state of the variable x, and then it reassigns that x. Similarly, setchar of x something, what it does is that it actually takes the current state of this list and it modifies that state. Yeah. So we will see more of this side effects in the coming classes. Yeah. So did you try out this program in your laptop? Otherwise, we can do that now. Hello. Hello.
Which one, sir?
The hash table.
No, sir.
Okay, then let's do that hash table ADT now. Let's define. So they are actually talking about two different ADTs. One is a vector ADT, one is a hash table ADT. Yeah, let's implement both. So what is a vector ADT? So you have make vector, then vector ref, and vector set. Okay, so this has type. It takes two arguments, number and a. Make vector, so it takes number and a value, and it gives you back vector with that many locations. Okay. Okay, let's just write it as vector. And the second one is takes a vector and a number. And the value stored at index. And the third one is vector number stores and a value. Value stores value at the index of V. Okay, so we have, so can you quickly make, how do you implement this? I don't think they have given an implementation in this, yeah? Have they given an implementation? No, they haven't given an implementation in this. Yeah, so let's try to quickly implement this. How do you implement this? How can you implement this? It's a fixed size collection with indexed access. So it's like an array. Yeah, this is an array. Vector is nothing but an array. So how do we implement a fixed size array? Can somebody tell me? Hello? Hello? Somebody? How do we make a vector? So for instance, I want to say something like make vector, then 10 and value 0. So that should give me, let's imagine it is a list which contains 10 zeros. Yeah. So one possible implementation could be something like, I could have a list which contains a tag called vector and this, and a list which contains this. Yeah. This could be a possible implementation. So tag which contains vector and then some 10 zeros. And then vector ref is nothing but you just strip off, take the color and okay. Yeah, so how do we get the 10th element? How do we get the 10th element? In a list. Hello?
You can keep on coloring.
Yeah, you have to walk down the list. You just have to walk down the list. And vector set. Yeah, so why don't we write down these three functions? Make vector and vector ref and vector set quickly. Are you doing it? Who is going to help me? I'm going to do. Who is going to help me? Let's ask. Who has a mic? Pulaksh. Pulaksh. No mic. Deeksha. Deeksha. Pratiksha. Are these people here or they just, hello? Are they writing in the chat? Sir, I'm watching on YouTube because of also the shift Zoom. Okay, that's fine. Bhavana.
Yes, sir.
All right, let's do this. So let's make vector, define make vector. So let's call it number val. What should be this? Let's also call vector tag. Define vec tag. So what should be the tag for vec tag?
It's a vector.
Yeah, just vec. What could be this?
Sir, if number is greater than 0.
Yeah, but let's just cons of vector tag. And let's use a helper function. Make vector helper num val. Yeah, and make vector helper num val. Okay, should be if
The num is greater than 0. It is greater than num with 0.
0, then
Then cons.
cons.
Sir, I guess we have to use append here because we want number of zeros. So use
Yeah,
append.
append. Append.
And
No, you could
well,
use cons here. Why not? You could just append it to the beginning, no?
other sir, then this vector tag will be in the behind, right?
Now, what you could do is that if num equal to 0, then you return an empty list. So this is one thing which you have to always remember. Sometimes it is always better to start with the base case of your induction always have to be nil. Okay. I mean, even when you write proofs, it is always better if your base case is always a vacuous case. That's the vacuous case is the empty list in our case. Okay. So if num equal to 0, then you return nil. Otherwise, you cons val with you understand what I'm saying?
Make vector helper
Yeah.
num -1.
And val. Yeah. Okay. So let's see what is make vector 10 0. Yeah. So it's something with a list. It's a symbol with a list of 10 zeros. Okay. So that's fine. Okay. So that is make vector helper, make vector. Now let's do vector ref. Who's going to help me? Hello. Devansh.
Yes, sir.
Yeah.
Okay, so we need to get a valid index number. Uh,
Yeah.
okay, yeah.
No, we need a vector first. We need a vec. Okay. We need a vector and then we need a number. Yeah.
Okay, so we need the value stored at the num. Okay,
Yeah.
yeah. Okay. Uh, so we need to go to the particular vector,
Yeah. No,
and
no, no. But
when
no, no, no. First, what? First, we need to do what? We need to strip down that tag.
Scattering.
yeah, we need to start considering the vector.
Scattering.
And define them, and yeah.
Yeah. Now.
Yeah, if if it is equal to uh, if the car of a vec list is equal to num.
No, 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 no. Num here is the index. Okay.
Okay.
Yeah.
Okay, it's ending. Uh, so we need to keep track of the index, right?
No. What should be the base case here? If num equal to 0 is the base case here, yeah? Num equal to 0, what do you do?
So like this num is the index, and why this needs to be the base case?
Because we are doing this one again recursively by walking down the list.
So like we can keep track of this thing, like at this particular index, if we get the we can keep track of the indexes, no, like starting from the top to bottom. If we reach a particular index, then we can return that one.
I didn't understand.
Like if num is the index that we need, then we can only just keep track of the index that we are traversing, instead of going throughout the list.
How do you
Like
how do you track the particular index in a list?
uh, like starting from, like, we provide the vector f helper as the length of the list,
Mm-hmm.
and starting from the top, okay, like first index, and when we reach that index equal to num, then we can return that particular element.
Yeah, exactly. So if index equal num equal to 0, what do you return?
Okay.
So char
Okay,
of
for the
what
number
is?
equal to 0, we can
Yeah.
return the car of the vec list.
Exactly. Care of now. Care of vec list. Otherwise, you do vector helper.
F helper, we can go vec list num -1.
Yeah. Cadre of the vec list.
Cut off vec list, yeah, num -1.
Okay. So that is vector ref, and now vector set.
Sir, I didn't understand that. Why num -1 you are taking again?
Num -1, because initially imagine you have to look at the fifth element. In that case, what will you do? You start with the you color the list once, and you color the, and then you subtract the num also, the index also by 1. So when the index becomes 0, then what is your the car of the list will be your value. Get it?
Fine, fine. Got it. Sir, can you run it once?
Pardon?
Sir, can you run it once? Can you take an example?
Yeah. So, but let's do the vector set also. Then vector
In the vector, it should be vector, not color of vector. Vector is helper.
color of
No, sir, in vector, yes, you have written vector of helper, color of vector, right? So it should be vector only.
why it should be vector? It should be color of vector list, no?
Not this line, sir, not this line above this. So the hash defines vector ref, not vector reference. Vector.
So in vector f helper, that should be vec or CDR vec, color vec.
It should be color vec because we have a tag in front of the vector.
Okay.
Yeah. This is our internal representation. There will be a vector,
It's
then
11 o'clock.
followed by something.
Okay.
Yeah.
Yes, sir. Okay.
So I have a doubt.
Yeah.
If the vec list becomes null before num becomes 0, then char of vec list will throw an error.
Yeah, it will throw an error. Very good. Very good. So how do we do that?
So you'll have to check if the
But you have to understand that the point is that the thing is that here we are not checking that num has to be smaller than the size of the make vector. Okay, because when okay, so let's make vector. Let's make it this way. List of, we are changing our representation. Okay, we just change the representation. So now if I say make vector 10 2, then it will have a, what will be written there? It will be a vector followed by 10 2s. What happened here? Make vector 10 1. Okay, yeah, it is working fine. I hadn't. Okay, so what I did is that I just added the num also. Now when we here, what we can do is that if, what should I do here? If cadre of vec so what is less than or equal to in scheme? So should we put it as now? Yeah. Are you following what I'm doing?
No, sir. Can you repeat?
So what I'm doing is that, so Devani asked a question. Uh, Yeah, so what I'm doing is that, so my representation for my vector is initially a tag, then a size of the vector, then followed by the vector representation. Okay, so that is my new representation. It's a list which contains vector tag followed by the size of the vector and then this one. And now when I'm reference the vector number, I can actually check if my number is actually within the size of this one. So I actually am checking if num is smaller than cadre of vec.
The length of that list, I think.
Pardon?
Sir,
Is it fine now?
oh,
It's not? Yeah, so here there should be a bar. So if I say define v1 to be make vector 10 to, and if I say
Sir, if the
yeah,
number is greater than cutter of vector, you should display.
yes, greater than or equal to, yeah,
You can put directly, yeah.
vector ref v10 should give me an error. Now what is it? V1. Vector ref v1.
So num also, you have to give num also.
Yeah, vector ref v1 10 index out of bound. If I give 2 now color of vec and num. Oh, what vector ref helper vec list. It should not be vec list, it should be cadre of vec list. Great. What happens? What is going on? Can somebody help me? What is wrong with this? Cadre of vec, no?
Your cadre of cadre will be a list of list.
Okay, cadre of cadre. Okay. Yeah, I hope this one will work. Vector list, vector ref v1, 2. Okay, perfect. All right. Okay, so that's how we got vector ref. And now how do we do? We have only time for vector set. How do you do vector set? Let's copy. Now define vector set vec num val if greater than or equal to num display vector set helper vec list num val will be if equal to num 0. If equal to num 0, what should we do?
Set char
Set char what?
val
Vec list val. Yeah. And otherwise vector set helper vec cadre vec list minus num val. Vector set v1 to 20. V1. Okay. Vector set v1 to 30. v1 vector set v1 340. Yeah, so it is working fine. Yeah, clear? All right. Hello. Okay, so now you have to use this vector to do the hash table. Hash table implementation is given here. Hello, but you have to practice. Okay, otherwise it's not very easy. Hello.
Yes, sir.
Yes, sir.
Okay, so for next week you have to do. You have to show me. You have to come prepared with the lecture 12, and you have to do those two exercises: and 8 queens, n queens, and knight's tour, and yeah, lecture 12. Okay. All right then. Hello.
Yes, sir.
Any questions? Any questions?
No, sir.
Yeah, if we finish, I have to. I mean, I would like to finish this book by by the end of this month, or and then we can do some other stuff like prologue and things like that. Okay. All right. Thank you. So please speed up a bit. Okay. All right. Thank you.
Thank you, sir.
Bye.
Thank you, sir.